In this section, we're going to review using the Phasor domain technique to map a system input to a system output. Throughout Chapter 5, we're going to expand this technique, building on some things we've learned in signals and systems in order to tackle more complicated types of signals. So in this section, we're focusing on the Phasor domain, which, as you remember from circuits, focuses on a sinusoidal input. And it gives us a technique to find the corresponding sinusoidal output when a signal passes through a system with a magnitude change and a phase shift, but no change in frequency. So those are properties that apply to all linear systems, linear time invariant systems. What we're going to do as we progress through the chapter is we're going to expand this into two major techniques. The first is going to be the Fourier series approach. And the Fourier series approach is going to work for any periodic input. So we're going to apply superposition to build up any periodic input and apply a system response in a structured way, building out the Phasor technique. Then what we will do in the second half of the chapter, roughly, is what's called the Fourier transform approach. The Fourier transform approach is developed for non-periodic signals. So it's going to let us remove the restriction and apply our linear analysis techniques and or frequency response of a system. So although this focuses on non-periodic waveforms, we're also going to see it still works for periodic waveforms. So these two Fourier techniques together are the basis of a whole lot of linear time invariant system design. What they do is they allow us to focus on frequency as our target variable for design, as opposed to focusing on time, which is what we're used to doing when we have a signal being a function of time. So we're going to see in Chapter 5, we really learn to blend these two views of a signal into a complete approach to signal processing. Now, getting on to our review of the Phasor domain technique. If we have a signal x, which is a sinusoid, and we want to represent it in the Phasor domain, what we do is we say, well, the signal, when we talk about phasors, we talk about real signals, but these real signals are based on two complex parts. The first part is what gives us the frequency. So as you remember, a phasor corresponds to a specific frequency, omega. And then we have the complex number, the phasor, right here. The phasor is equal to a magnitude and an angle, phi. And if we then take that expansion and say, well, what does this mean for the signal x of t? We see that by properties of the exponential, that this e to the j here with omega t and phi, and the magnitude of x is just a real number itself, so the operator that takes the real number does not change it. And now if we simplify further, we see that we have this magnitude x, which comes from the phasor, And the real part from Euler's formula of that exponential is just the cosine of the phase term, omega t plus v. So we recall that the phasor is giving us, through its magnitude, the amplitude of the cosine, and through its angle, the phase shift of the cosine. As another example, if I have a signal that is represented as a sine wave, say a voltage sine wave at a frequency, and I want to put this in terms of a phasor, we need to rephrase it in terms of a cosine. So the sine is the cosine delayed by 90 degrees. So we rewrite it as a cosine. And we delay the cosine by pi over 2 to make it the sine. Now again, we have a magnitude and a phase, so we can say that the phasor for this is V0 at an angle of minus pi over 2, or if I write that in complex exponential form, it would be V sub 0 e to the j pi over 2. The phasor domain also makes it convenient for working with derivatives and integrals, which often come up in our linear systems, of course. As an example, let's say I have a current waveform, which is the real part of a current phasor I at some frequency omega. And my expression calls for derivative of current. So now I can simplify what's on the right-hand side of the equal sign. The fact that you are taking the derivative of the real part of a quantity, I can interchange those operations. I can take the real part of a derivative, and I will get the same quantity. There's a number of ways to look at derivatives with respect to time of complex quantities, but one of the most direct ways is just to consider the real part and the imaginary part as corresponding signals. Take the time derivative of both, and you will have the correct result. So I take the real part of the derivative of I e to the j omega t, and now if I focus on the derivative inside, I see that the quantity I is a constant, the phasor I. So I will have an I here when I take that derivative. And now I just have to take the derivative with respect to time of e to the j omega t. It's a complex exponential, so I have e to the j omega t, and the multiplier of t, or the variable I'm taking the derivative with respect to, so that j omega comes out front, and I still have the real operator right there. So my result has phasor j omega I. So when you take the derivative with respect to time in the phasor domain of some quantity, in this case we did I, you get j omega times the corresponding phasor. Similarly, we can prove, and your book has a few more details on this, that if I take the integral with respect to time over the time variable, that is the same as dividing by j omega. So you take the phasor you started with, and we divide by j omega. Now let's use the phasor domain approach to solve a differential equation for a sinusoidal input. So let's do this differential equation. Second derivative of the function y plus a times the function y itself is equal to the input function x of t plus b times the first derivative of the function x of t. And let's go ahead and turn this into the phasor domain. So we know that when we take the derivative, I get j omega. So if I take the second derivative, I get j omega squared, the phasor for y. Here I have a plus the phasor for y, and the phasor for x will be capital X. And then I have plus b times the phasor for the signal x of t. So that will be j omega times the phasor x. And we want to solve for the phasor y. So we'll factor out the x and the y from each side here. So factoring out y, I have j omega quantity squared, which is minus omega squared. And I have an a, so I have a minus omega squared. And let's factor out x on the right-hand side. I have 1 plus j omega b. And then I can solve for the phasor y by dividing out the term. It's equal to x times the fraction 1 plus j omega b over a minus omega squared. Now let's go ahead and substitute in some specifics. Let's let x of t be equal to the signal 5 sine of 2 pi times 50 t. So we have a 50 hertz signal plus 30 degrees. And now we want to write that in phasor form. So the first thing we do is change it to a cosine. So we delay the phase by 90 degrees to get the cosine. So 5 cosine 2 pi 50 hertz times t minus 60 degrees. And now I have a couple quantities I can extract from this. I have omega equals 2 pi times 50, or the frequency is equal to 50 hertz. And my phase is minus 60 degrees. And if I put that in radians, it's going to be 1/6 of the way around the circle. So minus 2 pi over 6, or minus pi over 3. And I can write the corresponding phasor, which is going to be 5 at an angle of minus pi over 3, or if I write that in exponential form, 5e to the minus j pi over 3. Let's let the parameter a be equal to 2 times 10 to the 4th, and let's let the parameter b be equal to 5 times 10 to the negative 3rd power. Now let's figure out what this system factor that is affecting the input phasor x is based on these parameters. So this factor is going to be 1 plus j omega b. So j times 2 pi 50 times 5 times 10 to the minus 3rd over the parameter a, 2 times 10 to the 4th minus omega squared. Omega is 100 pi, so we get 10 to the 4th pi squared. So simplifying that, in the numerator we have 1 plus j, and there we have 2 times pi times 50, so that's 100 pi times 5, that's 500 pi, and then we multiply times 10 to the negative 3rd, so 0.5 pi. And then in the denominator, we have a 10 to the 4th term in each of those, and then we have 2 minus pi squared, so it's going to be a negative number, negative pi squared minus 2 times 10 to the 4th. And if you run that value through a calculator, you will get minus 1.27 times 10 to the minus 5 minus j, 1.996 times 10 to the minus 5. And if we write that in polar form, we get 2.37 times 10 to the minus 5 at an angle of minus 122 degrees, or put it in radians if you prefer. And now that we have this factor, we can multiply that times the phasor for x. So let's call this phasor here h, the ratio between y and x. And let's figure out then our output phasor is going to be our input phasor times this phasor h. And our input phasor is 5 at an angle of minus 60 degrees. And we multiply that times 2.37 times 10 to the minus 5 at an angle of minus 122 degrees. And we have it in polar form, so that's convenient. We get a magnitude of 1.18 times 10 to the minus 4, and we add the angles together, and we get an angle of minus 182 degrees. So that is our output phasor y. So that tells us our output y of t is going to be, let's write it in millivolts, so 0.118 millivolts. It's a very small quantity, times a cosine of, again, we keep the frequency, so 50 hertz, with a phase shift of minus 182 degrees. In the next section, we are going to move on to something called the Fourier series. We're going to show for any periodic input, we can use superposition to represent it as a sum of sinusoids at a variety of frequencies. Then using superposition, we will find the output using the phasor technique, and we will be able to find the net output overall. So that is the technique that we're going to spend about half of the remainder of Chapter 5 developing. It's a phasor domain technique, so it's for periodic functions. And then in the second half of the chapter, we will extend that technique to work even for input signals that are not periodic.